Alright, so here's where we get to some real equations. So all the videos so far have pretty much just been like a brief overview of neat concepts in fluids. Well, here's where we're going to get to Bernoulli's equation, and you'll see it's really like our energy equation, but for fluids. It explains almost everything fluids. So, key principle right off the bat, the mass of a flowing fluid does not change as it flows. So this means that for an incompressible fluid, an ideal fluid, what we're considering, that if the cross-sectional area of that fluid is flowing through changes, if that area changes, the speed that it flows must change proportionately to keep the same volume of fluid passing through that area per time. So V dt 1 is equal to dV dt 2. So for an incompressible fluid, the change in volume, the amount of volume of fluid passing through an area per unit time doesn't change. And so this is A1, B1 equal to A2, V2. And if the fluid is compressible, and therefore it's not an ideal fluid, then this equation just has to take density into account. So for a compressible fluid, then you just add density to that on either side. And the density changes. A2, V2. There's an equation, which I mentioned, called Bernoulli's equation that relates the pressure, flow speed, and height for flow of an ideal fluid. Bernoulli's equation is the energy equation for fluids. It states that the work done on a unit volume of fluid by the surrounding fluid is equal to the sum of the changes in kinetic and potential energies per unit volume that occur during the flow. So let me write this out, write Bernoulli's equation out, and you just tell me if some, all, or none of this equation looks familiar. So we have pressure 1, talking about fluids, plus rho gy1, what does that look like, plus 1/2 rho v1 squared, what does that look like, is equal to P2 plus rho gy2 plus 1/2 rho v2 squared. Does any of that look like anything we've seen before? Of course, we haven't had density in there, but can you tell which part is the gravitational potential energy portion? Right, like mgh, right? And which part is the kinetic energy part? Like 1/2 mv squared. So notice that if the fluid is not flowing, the kinetic energy term disappears, right? No velocity. And we're left with a pressure relationship, which is useful. So if we take out this guy, no kinetic energy, it's not flowing, then we're left with P1 plus rho gy1 is equal to P2 plus rho gy2. And we can rearrange that and say P2 minus P1 is equal to minus rho g y2 minus y1. And if we take point 2 to be the surface of a liquid, right? Talking about some container and it has water in it. If you take this to be point 2, so this is like y2, and some depth that we're interested in to be y1, then it simplifies even farther. we could just say P, because P2 would be 0, is equal to P naught plus rho GH. I'm sorry, P1 would not be 0, it would be P naught. So the pressure at the top. But rho GH, H being the height, or the depth, I guess. And this is where the first law we encountered in this whole lecture came from. This is where Pascal's law was derived from. So now, finally, how do airplanes stay in the air? What causes the lift, the upwards force on the wings of the plane? It's all to do with Bernoulli's equation and the shape of the wing. So I'm going to put these up and we're going to read through it together. Because there's, just like with rockets, there's common misconceptions with why planes fly. All right, lift on an airplane wing. Let me make sure this is readable for you. Not at all. Is that better? New. One more try. All right, cool. Lift on an airplane wing. That's close enough, you can read that. So this other figure, which I have here as well, I think. Yeah, here. This figure here shows flow lines around a cross-section of an airplane wing. The flow lines crowd together, let's talk about this one, above the wing, corresponding to increased flow speed and reduced pressure, just as in some other example which we did not talk about. Hence, the downward force of the air on the top side of the wing is less than the upward force of the air on the underside of the wing, and there is a net upwards force, or lift. Lift is not simply due to the impulse of air striking the underside of the wing. In fact, the reduced pressure on the upper wing surface makes the greatest contribution to the lift. And this ignores vortices. So there's little pegs here that can exist on the top of wings that prevent the air from vortexing too much. But ignoring all that, we can also understand the lift force on the basis of momentum changes. The vector diagram, which I just threw away, shows that there is a net downward change in the vertical component of momentum of the air flowing past the wing, corresponding to the downward force the wing exerts on the air. The reaction force on the wing is upward, as we concluded above. Similar flow patterns and lift forces are found in the vicinity of any humped object in a wind. Moderate wind makes an umbrella float. A strong wind can turn it inside out. At high speed, lift can reduce traction on a car's tires. A spoiler at the car's tail, shaped like an upside-down wing, provides a compensating downward force. So a misconception about wings. Some discussions of lift claim that air travels faster over the top of a wing because it has farther to travel. This claim assumes that air molecules that part company at the front of the wing, one traveling over the wing and one under it. Let me bring this figure back out here. Must meet again at the wing's trailing edge. Not so. This figure here shows a computer simulation of parcels of air flowing around an airplane wing. Parcels that are adjacent at the front of the wing do not meet at the trailing edge. The flow over the top of the wing is much faster than if the parcels had to meet. In accordance with Bernoulli's equation, this faster speed means that there is even lower pressure above the wing, and hence greater lift than the farther to travel claim would suggest. So there you have it. There's a lot of misunderstandings of how wings generate lift, but a quick study of Bernoulli's equation and the physics of what's going on can dispel some of those. All right, that's it for this lecture.